In 1850, Hermite showed that if f of x written as the product x transpose a x is a positive definite quadratic form in n variables, namely x is in Rn and A is n by n matrix. Then there exists an x that is a integer non-zero vector such that we have the following estimate for the value of fx. This is bounded by some constant c sub n times the determinant a raised to the power 1 over n. So here c sub n is a constant that only depends on n. So this is the year 1850. In the year 1891, the story of our hero began. Minkowski found a new and more geometric proof of Hermite's result. And moreover, in his proof, he actually gave a much smaller c sub n, especially when n is large. And this is only the end of a beginning. Soon after, in the year 1893, Minkowski noticed that his proof was valid not only for this special case. So what is this special case? Specifically, geometrically. If you think of this geometrically, those x satisfying this inequality form an ellipsoid in the n-dimensional space. So this f of x, which is written as x transpose times a times x, where a is positive definite. This condition is very important. When a is positive definite, this quadratic form less than or equal to some constant will represent an ellipsoid in n-dimensional space. And Minkowski realized that his proof actually works not only for this n-dimensional ellipsoid, but for, this is the most important part, any convex body which was symmetric about the origin. And this led him to a large body of results that laid the foundation of a new branch of math called the geometry of numbers. And by geometry here, we really mean the convex geometry, namely the convexity. And this convexity made its first appearance in the Minkowski's convex body theorem, which we are going to talk about today. The Minkowski's convex body theorem basically says, if you have a convex body that is symmetric about the origin, then as long as this body is big enough, then it must contain a non-zero integer vector, like in here. The Minkowski's convex body theorem has a lot of applications, in particular in number theory. In this lecture series, we'll mainly focus on its application to the Diophantine approximation problem. In particular, we are going to prove the Dirichlet's simultaneous Diophantine approximation theorem using this. So now, come with me.